welcome everybody to my talk. You have become the very thing you swore to destroy. It's about remotely exploiting an antivirus engine. Let's just get this out of the way. My name is Simon. I am part of the cloud vulnerability research team at Google. I live in Zurich and I like to exploit both memory corruption and logic bugs. So let's get right into it. The AV engine we're going to exploit today is called ClamAV. It's an open source AV engine that runs on Linux, macOS, and Windows, and it's popular for Linux clients. It's widely used in server-side context, so that could be, for example, email servers. If you set up an SMTP server, there are tons of tutorials on how to make all emails getting scanned by ClamAV once they arrive. It also comes pre-installed with some email solutions, for example, Zimbra. It also comes with some appliances, so Cisco confirmed that the vulnerabilities we reported to them affected their Cisco Secure Web Appliance. So in an extreme case, if you compromise ClamAV, you can control the organization's network traffic. And then it's also just somewhere used in the back end of custom pipelines, for example, cloud storage pipelines or web forms. Anywhere where you can upload a file, it might get scanned by an AV engine before it's finally stored. And it's written in C, which makes it perfect for memory corruption, and that's what we're going to talk about today. So just to summarize, achieving a remote code execution would give an attacker privileged access to highly sensitive data, such as emails and up and downloaded files. So let's get into just a very high-level overview into how ClamAV works. And it supports file type detection. So whenever it receives a file that could be with the CLI or from an email server, it will try to detect whatever the file type is, and then it will either recursively unpack the file. So if it's, for example, an archive, like a zip file, it will unpack it and then detect each of the subfiles files and then scan them for viruses. And the recursive depth and number of files just depends on the configuration settings. So this diagram is basically exactly what I've just been talking about, where the file type is detected first, and then it internally basically just executes a giant switch statement for all of the different file formats that it supports. And there's about 50 of them at least. And if this file type is a container, so again, could be an archive, or for example, GPT is considered a container, in that case, it will scan all of the partitions inside of the GPT partition table. And once it goes into this recursive loop until it actually encounters an L file or a portable executable file, and in such cases it tries to actually detect the virus. In this case, I don't want to go into too much detail about how they detect viruses because it's not relevant to the exploit, but this could be simple hash matching and up to more complex pattern matching. So this brings us to the threat model. Let's say an external or internal attacker can somehow make a victim running ClamAV run a maliciously crafted file. So again, this could be a multi-tenant server model where one ClamAV instance is used to scan the files of multiple users. It could also be if there's a client-side ClamAV instance configured to download any downloaded files. So if a victim would browse to a malicious website where a file would be downloaded in the background, an attacker would somehow be able to make a victim scan a malicious file. And the attacker would then discover a vulnerability in the parser for one of the many file formats that are supported. And again, there's at least 50 of them in the documentation mentioned. And some of these are quite complex, for example, HFS+, or DMG, or CPIO, and there's many more. And then once they get the file scanned, they trigger and exploit one of these vulnerabilities that the attacker finds. So let's get into the agenda for today, and we're going to talk a little bit about the problem that I encountered. So I started off finding a buffer overflow, and then what I needed was an info leak, and I realized very quickly that that was going to be difficult. So we're going to talk about why the usual approaches to info leaks won't really work with remote ClamAV. And then I'm going to go into more detail about the bugs that we found, and then we're going to come up with an exploitation strategy that defeats the constraints that we talked about in the first step. And then afterwards, we're going to do a real-world case study about unauthenticated RCE on an email server. So why do common info leak strategies not apply to ClamAV? Let's start off with the assumed environment. So we're going to assume full ASLRs apply to all the loaded libraries and files, and an attacker gets to see the scan result, so they can see if the scan resulted in a virus being detected or not. And ClamAV runs in the upstream ClamD version, which is just the multi-threaded server mode. What that will also mean is that a single segfault will crash all the threads. So just to overly simplify, what happens if you have an info leak and then a memory corruption chain is you usually have some kind of two-stage approach, where as an attacker you send some kind of info leak trigger to a remote server, and that could be anything. That could be an out-of-bounds read, that could be use after free that somehow leads to uninitialized data being included in the response, too much data being returned. This could also be a file read where you read proc self maps, things like that. And then once everything goes well, the target will respond with some kind of information the attacker can use to then, in a second stage, craft a file that will trigger some kind of other memory corruption issue, probably along with some RobChain gadgets, and then the attacker, if everything goes well, receives a reverse shell. And while this is, of course, very simplified, this is usually the flow of having an info leak plus a memory corruption trigger. So this doesn't apply to ClamAV, because the problem is ClamAV is a non-interactive target. At most, an attacker can see if the scan resulted in a virus being detected or not. And in most environments, realistically, you're not even going to receive this information. You're just, at most, going to receive a custom error message. There is no direct interaction with ClamAV. So just to put this into the visual form, if we send an info leak trigger, if we found an out-of-bounds read in ClamAV and uploaded a file, let's say, to a web application, and we actually managed to successfully trigger the out-of-bounds read, but ClamAV, in this case, will just respond with a virus was found. And usually that's not even a string, that's just a Boolean value. And then the web application will just respond with a generic error message string. So that made it pretty difficult to just use a normal out-of-bounds read, for example. So before I get into the actual bugs, I just want to consider the alternative approaches that I could have taken and why they didn't end up working. So for one, we could have tried a partial pointer override, where instead of overwriting an entire function pointer to gain RIP control, we just overwrite a few bytes to make it point somewhere like system. But in those cases, you have to get kind of lucky that there's a function pointer that lets you do this, and where the first argument is a controlled string. And it just didn't work out for me, and I didn't find any gadget, at least none that were reliably. The second case are data-only exploit. And this is something that is interesting in the case of ClamAV, but it has some restrictions. So for example, ClamAV dumps the files before it scans them to disk, for example, when an archive is encountered. And it uses just a randomized string to store the file name. And this randomized path is actually stored on the heap. So if you had a heap buffer overflow, in theory, you could try to overwrite this heap, this path on the heap. And then you could force ClamAV in some file formats with some weird magic to cause an arbitrary file read. And this could work. The problem is, by default, in the upstream version, the files are going to be created with the ClamAV user. And this just won't work in a sandbox environment. Although it could work for targets where the environment is known and can be exploited. And then last but not least, you could just go the naive route and brute force ASLR. But again, it runs in multi-threaded server mode, and once the server has to restart, it has to download signatures, and it will take minutes to restart, so this is just not feasible. So let's get into the bugs. The first bug is a pretty classic heap buffer overflow, and in February of 2023, Cisco released an advisory on a heap buffer overflow that we reported. The CVE is 2023-232. And the CVS score was given by Cisco for 9.8, and that was because it can be triggered remotely by an unauthenticated attacker in default configuration. And by unauthenticated, I mean it's just once you get a victim to scan this file, the bug triggers. So that could, for example, as mentioned earlier, be if a file is downloaded from the browser and is automatically scanned, the buffer overflow will already trigger without a sandbox. And it happened while parsing HFS+, which is a file system developed by Apple, and it happened due to a missing bounce check. I don't want to go into too much detail about this particular bug, because the buffer overflow itself is not very interesting, but I just want to provide quick context, because we're using this buffer overflow to override a function pointer later. So the first thing to look out for is the read size variable, which is initialized with the value volume header block size. And the volume header is just the first 1024 bytes of the HFS+ file, or of the file system, and the block size is an attacker-controlled value. The only check that is being done here is that this value is a power of 2, and that it's in the range of 4 kilobyte to 2 megabyte. And then a few lines down below, we read size bytes into buffer, which is the variable buffer from the mmapped file. And buffer is an attacker-controlled, well, the size of buffer is also attacker-controlled and also comes from the volume header. And there was no check anywhere that read size was smaller or equal to buffer, which means this is a fairly standard heap buffer overflow. I think the only reason it wasn't found already was in order to reach the HFS plus parsing code, it had to be wrapped inside of a GPT partition. And I don't think any of the existing fuzzers like OSS fuzz were actually generating files like this. So the bug is quite powerful because the overflow size can be controlled, again, with some reason. And the overflow contents can also be arbitrarily controlled. So there's no restrictions like null bytes, for example. And we can trigger this bug basically as many times as we want because we could provide a zip file which is with as many of these HFS plus files as we would want. Now the second bug that we found is way more interesting. And we're going to end up exploiting this one, even though I said earlier an out-of-bounds read is pretty hard to actually exploit. So we reported an out-of-bounds read bug to the maintainers of libmspack in the same time frame. And libmspack is used by ClamAV to parse Microsoft cabinet files. So these are cab and CHM archives. And the CVE for this one is 2023-29077. And this can also be triggered remotely in default configurations. And this out-of-bounds read occurred due to integer truncation. So before I get into the actual source code details of this bug, I want to provide a little bit of background on CHM archives, because the way they are unpacked and the flow of unpacking them becomes pretty relevant to the exploit later on. So CHM are Microsoft compiled HTML help files. So they will bundle, for example, ebooks or just multiple HTML files for help, for documentation, etc. And this archive can contain compressed and uncompressed files. And it consists of a CHM file header, which contains some information like what version of CHM is this file, some metadata, and then, for example, the date when this archive was compiled. And then there is an array of file headers where each file header maps to one file. So the file header will contain the file name, the length of the file, the offset of the file within the archive, and then if the file is compressed or not. And then there's two types of files. There are system files, and these are files with a predefined name that contain metadata, for example, about expression. So not all the information about the CHM archive is stored inside of the actual header file, but some of these are stored in some uncompressed files within the archive with a predefined name. And then there are the actual content files, which contain the actual content, what should be scanned by ClamAV. So I want to walk through the visual process of what it kind of looks like on a very oversimplified level when an uncompressed file or when a CHM archive is extracted and when an uncompressed file is being read. So once the file header is being read, we can see on the right-hand side, we can see the source code libmspack uses to represent one file in memory. And we can see the first member is a next pointer, which indicates that it just builds a linked list of all the files. And then it uses the linked list to traverse all the available files. And the section pointer points into the uncompressed or into the compressed data section. And then we have an offset, which is just an attacker-controlled 8-byte value. And this offset basically just points into the uncompressed data section for an uncompressed file. And then libmspack just reads length bytes into memory. So it just allocates a buffer with malloc and then reads however many bytes into that buffer. So that process is quite simple, but it does get a little bit more complicated once a compressed file is encountered. So the file offset that the attacker controls is not used as an offset into the file directly, but it's used as an index into the reset table. And the reset table is one of these special system files that I mentioned earlier. So for example, if you see at the bottom, the very last line, this is the name of the reset table. So it just traverses the linked list and tries to read this file into memory. And the reset table contains the real offset of the decompressed file within it. And it's just treated as an array by libmspack. So let's say we traverse the linked list and we encounter a compressed file. What's going to happen is that libmspack just reads the reset table into memory, and then it uses the offset to index into this array, which then obtains the real offset into the compressed data section, and from here we can just read and then start decompressing. I do want to mention that this is a bit overly simplified, and in reality there is a good reason why you have this extra level of indirection, but I don't want to go into too much detail because it's not relevant to the exploit what exactly the compression algorithm does. All we need to know is that this reset table array contains the real offset within the file. So, as you might have guessed where this was going, is there is an out-of-bounds read in the reset table lookup. So libmspec treats the reset table like a regular uncompressed file, which means it allocates length bytes of memory according to the file entry, which is attacker controlled. However, it truncates the length field from 8 bytes to 4 bytes before allocating memory. And we can see this here. So we can see that the file length variable, which is attacker controlled, is truncated from an 8-byte signed of T type to just a signed 4-byte integer type. And in the line below, we can see the allocation where the data array is allocated. So let's follow this code with an example. Let's just say an attacker were to provide a length of value 1237 with the 32nd bit set, which results in just a giant value that you can see here. But once this is truncated to 4 bytes, the actual sizes will be 1237, which means the reset table buffer is 1237 bytes large. So let's follow this example. The problem is when a bounce check is made, when the lookup into the reset table is made, the untruncated length of 8 bytes is being made, which would be 1237 with the 32nd bit set. And that means simply that we can index way beyond 1237. So here's another example, and here you can see the actual lookup, where position is, let's say, 0xdeadbeef, which is attacker controlled, and it's the offset of the file entry. And the reset table, which is just our table length, is the giant untruncated value. And because that bounce check is made on that 8-byte value, we can bypass it and then index at the offset 0xdeadbeef into the 1237 bytes array. So this is a pretty strong out-of-bounds read primitive because the size of the reset table buffer can be arbitrarily controlled, which makes heap feng shui much easier. And we can also control the out-of-bounds read size, which can be either 4 or 8 bytes, and we can also control the out-of-bounds index, which makes this a lot easier. The resulting value of the out-of-bounds read is then interpreted as the offset into the CHM archive file. So libmspec will try to seek to this offset within the file. So let's use these two bugs to pawn ClamAV and see how we can get around the constraints that I outlined earlier. So let's start off with a couple of assumptions. Let's say we have a CHM archive file that contains a compressed known virus. In order to detect the known compressed virus, the CHM file must be well formed and libmspec must be able to seek to it correctly. So on the right-hand side, we can see the call to read reset table, which is the function which the out-of-bounds read actually triggers. And I want to pay special attention to the offset variable, which is passed as a pointer. And this variable will contain the value that we read out of bounds. For example, that could be a function pointer. And then a couple of lines of code later, we see that this unknown value, we assume that it is unknown, is added with 2 other attacker-controlled values. So these 2 values are also just part of some uncompressed files, and these are also 8-byte controlled values. And the final result of this addition is stored in the in-offset field. And then in the last step, libmspec will try to seek to in-offset, and then we'll start to read and decompress. So let's assume we can make a target ClamAV instance scan multiple files, or as many files as we want as an attacker. And let's just assume for now we can reliably prepare the heap in a way that the out-of-bounds read always reads the exact same value, which is still unknown. The only thing that we change in each file that we send are the 2 other values that we control. And that will yield in kind of random values because we have no idea what the function pointer value actually is. So that means the resulting value of this addition can result in basically 3 places that can be seeked to. So the first one, which is the most likely one, is that we seek somewhere outside of the file. And in this case, seek just returns an error, and ClamAV doesn't crash, it just stops the scan and returns, and no virus is found. The second case is that we seek somewhere into the file, but not at the beginning of the compressed virus. In this case, the decompression algorithm will likely just complain, return error, and no virus is found. And then there's a very small chance that the sum of the addition actually results in exactly to libmspec seeking to the beginning of the compressed virus, in which case the virus is detected. So just to visualize this, let's just say we just spam files, and the only thing we ever change are the two other values. We can seek, and at some point we seek to exactly the known virus, in which case the attacker will get a message that a virus was detected, and from there we can derive what the value of the function pointer must have been. So at some point, the sum of the offset addition with the function pointer is exactly the offset of the known virus in the file. In this case, it is detected. So this allows us to brute force ASLR or side channel ASLR without ever triggering the buffer overflow and never crashing the server. Because even if the out of bounds read didn't read the function pointer, it should never really crash the server if we just read a couple of bytes beyond the current buffer. So when the virus is detected, when the attacker gets the message that the virus was detected, because they know the other two values that were added, we know exactly what the value of the function pointer was. The only problem is, while this works in theory, we still have to brute force hundreds of millions of possibilities of ASLR, which means we would still have to send hundreds of millions of files, which is just not feasible, right? So there is a small trick that we used where we aligned the out-of-bounds read in a way that it read only 1 byte of unknown data. So we found a structure in memory that there was a function pointers and the 3 previous bytes were known data, or they were attacker controlled. So in this case, if you aligned the out-of-bounds read in this way, there was only 1 byte that was unknown, meaning 255 possibilities. So if you just upload 255 files and just change the 2 values that are added, at some point the virus will be detected, and that means you know exactly what the byte was. And then in that case, you can just realign the out-of-bounds read and go on until you leak the full function pointer. So just to summarize the ASLR bypass oracle, we use the value of an out-of-bounds read to change the logic flow of the target to side channel the value that was being read. So to kind of put this into like pseudocode, just to convey this concept a little bit more, we just have some kind of out-of-bounds trigger where a value is read out of bounds. And then this value is maybe not reflected back to the attacker in any way. It's just not possible to see what that value was. However, if some logic is performed on this value, there could be different code paths that are entered. And if an attacker can observe what behavior occurs from the application, they might be able to derive what the value was. So this will not work for every out-of-bounds read, but it does work sometimes. And I've encountered this a couple of times now that I am actively looking for it. And by aligning the out-of-bounds read offset with known or attacker-controlled data, we reduce the number of required attempts to roughly 1,000. So bytes were brute forced individually, and this yielded more control over the logic flow that we manipulated. So let's talk about making this reliable, because so far we've been assuming a very reliable heap room, which is actually quite difficult. So again, in order for the exploit to be reliable, the out-of-bounds read needs to be virtually 100% reliable as well, which depends heavily on the heap room. And this could be achieved when libc's allocator was used via the best fit behavior. I do want to mention, though, that I'm going to skip over a couple of problems I had finding this for time reasons, but this was by far the most difficult part of the project for me, was finding this reliable heap room, just because so many times I found one that was 95% reliable, and that just wasn't good enough for this kind of exploit to work. So I want to introduce DMG, which is the Apple disk image, another file format by Apple. And it's supported by ClimbAV, and it turned out to enable quite powerful heap pruning primitives. So a DMG file consists of a main header. It consists, those are just the first 1024 bytes, which contains information, again, such as the version, but also where to find an XML document inside of the DMG file. And this XML document describes the layout of the image, the actual partition, if you will. And then, of course, you have the actual data. So the XML document contains base64 encoded MISH blocks, and each MISH block describes a file in the DMG image. So that would be the length of the file, the offset within the DMG file, and is the file compressed, what kind of compression is used, etc. So here in this snippet, you can see what this XML could look like. The most important part is simply the data element, which again contains a base64 encoded string. So when parsing a DMG file, ClimbAV has the following flow of allocations and deallocations. It will walk the XML document until a base64 string is found, and then it copies this base64 string to the heap, and then it decodes it and copies the decoded struct to the heap, and then it frees the base64 string again. And once all of these steps are completed, once the entire XML document has been walked, each file is then scanned, and then the corresponding decoded struct is freed. So the following pseudocode, this is pseudocode that I wrote just to make this kind of a bit more clear. This is not actual ClamAV code. So in this code, you can see that the XML is extracted from the DMG blob, and then a linked list is created for all of the files inside of the DMG file, and then the XML is walked, and we find a data element, and we just copy the value to the heap. It's decoded, we put whatever was decoded, that a pointer to it, into the linked list, and then we free the base64 string. And then after all of this is done, we scan each of the files. So this is quite powerful because these base64 strings can be as large as we want, and we can spam as many of them as we want. It will just use the first few bytes and just ignore the rest of it. So this is a snippet from the actual exploit where I sprayed 1,016 kilobyte blocks. And these are the decoded structs. So the actual base64 string is slightly larger than this. And I don't want to go into too much detail about libc because there is a billion better resources out there. I just want to go into kind of the behavior that was observable and very reliable with this particular heap spray. So after spraying 1,016 kilobyte blocks, the following behavior was observable. So every time a mesh is allocated of 16 kilobytes, libc tries to find an existing hole. So that is a free chunk anywhere on the fragmented heap that could fit this allocation. And it will prioritize either a best fit, which means an exact fit, or it will try to find just the smallest possible chunk that it can fit this into. And if there's no chunk available, it will just place it at the end of the current arena, and if necessary, extends the current arena. So after some time, if you spray 1,000 of these structs, they will all be allocated next to each other because we just assume that all the fragmented heap, when we get our file scanned, we have no idea what the current heap layout is. But after some time, all available holes for 16 kilobytes will be filled, which means they all have to go to the end of the heap and will be right next to each other. And we can visualize this here, where the red represents the previous and the fragmented heap. And then we have all of the decoded meshes being right next to each other, being next to the top chunk, which is the end of the current heap. So let's cause some controlled chaos. And I'm going to throw quite a few numbers around here, but I'm going to explain and it will, in a few slides, and it will make sense. So after spraying these 1,016 kilobyte decoded structs, we allocate one of size 91,102. And this will lead to an allocation of a base64 string of size 121,472. And again, this will make more sense later, but this is what it will look like. Because we filled all of the 16 kilobyte holes previously, all larger allocations obviously also can go into an existing hole, which means they will also be allocated at the end of the heap. So the 121,472,000 byte string, base64 string, is freed right after decoding it, leading to a hole of the same size. So now we have created a free chunk. So for all future allocations, libc again tries to find the best fit, which means it will prioritize the smallest possible hole, which means the 121,000 byte hole should almost never be touched just because there are better free chunks available. So we can keep this chunk free until we actually need to allocate something into it. And if we can cause an allocation of 121,472 bytes, it will be placed exactly into this hole just every time. So now it was all about placing a function pointer into this hole. And for this, we needed to exploit just another file format. And in this case, we looked at the rich text format parsing that ClamAV supports. And an RTF file can cause recursive scanning states. So in the snippet here, you have ABC, and then you have curly brackets, and an object begins. And this object also contains another object. And because there are different types of objects, the parser state needs to be pushed to a stack. And to do this, ClamAV just allocates a stack to the heap. And every time the stack is no longer big enough to fit the parser states, it will reallocate the stack and cause a larger one. And if we do this, the stack will be exactly a number that we've seen before, 121,472 bytes large. So that means it will pretty much always go into this hole, exactly where we need it to be. And the reason I chose 121,000 is it's one of the smallest possible values. It's the smallest possible value of the RTF state stack to be as large as possible before mmap starts to complain, before malloc starts to complain about it. So once, I think it's 128 kilobytes, but that's also configurable. Once an allocation is larger than this, it will just be passed to mmap and it won't be placed on a normal heap. So this function pointer, or this state, contains some function pointers, which is what we're after. In this case, we're after the CB process pointer, and we can see a function pointer before. But however, some of the bytes were known because of the endianness. The upper bytes were just zeros. So the RTF stack contains the function pointers, and we can reliably allocate it into here. And after the RTF file is parsed, the stack is freed, but the memory contents are not cleared, which means the function pointer values will still be inside of that hole. And if we allocate the reset table buffer, from which we read out of bounds from, we can, with a size of 120,000, we get reliably allocated into the exact same hole, which means we can read uninitialized heap data out of bounds. So in this case, you can see here, we put the reset table buffer into this hole, and there's just a small bit of space that isn't allocated yet, and that's exactly where we read out of bounds from. So let's put it all together. We leak ASLR with the oracle that we discussed earlier. And then we prepare a ROP chain. So from here on out, it's fairly standard. So I don't want to go into too much detail about this. And then we need another heap room in order to overwrite a function pointer. But it was a very similar heap room, actually. And then we trigger the buffer overflow and overwrite the function pointer on the heap. And funny enough, we will just overwrite the exact same function pointer that we leaked earlier. So let's get into a real-world case study. And how to exploit this in the real world. Because so far we've been assuming that we can talk directly to a ClamAV instance, but that's usually not the case. So the target for today is Zimbra. It's an open source enterprise-ready email suite, and it comes with ClamAV installed by default, which means every incoming and outgoing email is scanned, and no sandboxing is deployed. Zimbra is commonly used by governments, and there was mass exploitation of different CVEs in the past year. For example, CVE 2022-27925, where Volexity reported on an exploit being used against government, military, and billion-dollar corporations. And then there was also a second exploitation. There's an article on a second exploitation campaign about Russian APTs targeting NATO-aligned government servers to access military and diplomat emails using another CVE. So let's just quickly talk about why the oracle won't work in an email context. Why can't we just plug and play what we have so far? So far, we have been assuming that a setup where an attacker will be notified of the scan result, which means was there a virus detected or not. And this is usually not the case for an email server as an external or unauthenticated attacker. So if you're part of the organization and someone tried to send you a virus, you might get some kind of notification. But if you're an external attacker, that won't happen. And what happens if you send a payload via email, the SMTP server will just reply with OK, and then queue the server for processing, and first send the email to ClamAV for virus scanning, and afterwards to Spam Assassin to be checked for spam. So the SMTP server simply receives the email and then queues it, and this makes timing-based attacks impossible because the queue is used. At least it just makes it very unreliable. So my idea was like, hey, maybe instead of putting a virus in there, I can put a file in there that will potentially hang the process, and then I can just kind of derive from the timing if I guess the correct function pointer offset. But again, because the queue is used, this didn't work. That means we need another side channel to leak the side channel, and maybe we can exploit the fact that virus scanning comes before spam checking. So just to give a very, very quick and much oversimplified intro on email spoofing validation, when an attacker or anyone sends an email to an SMTP server, they can simply claim to be anyone. They can simply claim to be, hey, I'm trusted at example.com. And in order to validate this claim, the email server that receives the email asks the responsible DNS server for example.com, like, hey, which IPs can actually send emails in your name? And when the DNS server responds with a list of IPs, it will validate that the sender IP is actually included in that list. So what we saw here, what we see in the bottom is a screenshot of this type of DNS record being asked. It's a TXT record for a subdomain from Burp Collaborator. And that's just sent from the Simbra setup. So in Simbra's configuration, the email server bails if a virus was detected in the email and then no spam checks are made. So that means an attacker can host a DNS server and they just generate a unique subdomain per email that they send to the target instance. And when a virus is found, which means the oracle did not succeed, a DNS request is made because it didn't bail from the spam check. And that's how we can find out when you receive the DNS request that the oracle was wrong. But if after some time no DNS request is ever made, we can be fairly confident that the oracle succeeded, which means the virus was found. So now it's time for a video I want to show right here. So in this case, we're running the exploit, we're spawning a DNS listener, and we're starting to send emails. And I do want to mention that this exploit, the video is heavily speed up. So the real exploit, I didn't optimize it, but it can run for 1 or 2 hours. So it takes a very long time. So usually when I tested the exploit, I started it and then went for lunch. And I hoped it worked when I came back. So now we're going to start brute forcing the byte. And any second now, the video starts to speed up. And we leaked the first byte after 32 tries. And that's how we know what the value was. And now the video will just continue and brute force byte by byte. So at this point, we have leaked the full function pointer of RTF object process, and that's how we can know what the location of libclimav.so is in memory. So at this point, we just start the reverse shell listener. Oh, and I don't know why that did that. Sorry. And there you go. So to get to the conclusions, just because the result of an out-of-bounds read is not directly reflected, it can still be side-channeled somehow by observing the behavior of the application based on the value. And this approach or this logic can also be used in scenarios where you target a load-balanced service. So for example, if you have an info leak of one worker, but you have no way of guaranteeing that your second stage will arrive at a second worker, you can use this to kind of make sure you could have, instead of embedding a known virus, you could have embedded a file that triggers the buffer overflow, and you could have made sure that the buffer overflow only triggers when the file is scanned by the correct worker. So we kind of internally call this conditional corruption, where you use the out-of-bounds read to make sure the exploit only triggers when the value is correct. So that's it. I think we're exactly on time. And if you have any questions, feel free to reach out, or maybe you have time for questions now.